All right, so this is the first and last video for section 7.3, where we talk about one-sided confidence intervals, and it will be hopefully pretty straightforward. So I want you to pause, copy, and play. So in one-sided confidence intervals, we just want like 95% of the probability to be on one side of a quantile, the other side of a quantile. So we could have an upper confidence interval or a lower confidence interval. And we'll go back to section 7.1 for this initial spot, okay? So let's take a random sample x1 through xn from a normal distribution where sigma is unknown. And we're going to try and find a one-sided confidence interval for the population mean mu, okay? So this is scenario 2 from section 7.1 with the sigma unknown, right? And we're just going to adapt that result, okay? So I've got my random sample, and I've got my unknown mu and sigma, and I want to find a confidence interval for mu. So I'm going to take Q to be the 1 minus alpha quantile, not the 1 minus alpha over 2. So let's say back in section 7.1, if I wanted a 95% confidence interval, I took 5% and I divided it by 2 and got 2.5%. And I went and looked for the 2.5% quantile and the 97.5% quantile. 2.5% off of 0 and 100, okay? With a one-sided quantile, with a one-sided confidence interval, I just want a single quantile. So if I want a 95% confidence interval, my alpha is 0.05. That means I want the 1 minus 0.05, the 95% quantile of the t distribution with n minus 1 degrees of freedom, okay? So remember, since I don't know sigma, I'm not going to use a normal distribution, I'm going to use a t distribution. Right. So then the lower confidence interval for mu is x bar plus q times s over root n as my upper value and negative infinity is my lower value. And if I want, so remember, to the left of q is 95% of the area. So x bar plus q gives me the 95% area to the left. And the upper confidence interval would be x bar minus q times s over root n up to infinity, okay? So if I wanted to know what spot has 95% of the area above it, I would take the negative value of the quantile, since the t distribution is symmetric. So for example, and this is data we've used in other examples in other videos, I've got the data 2.8, 3.2, 3.64, 4.8, and 5.1 is a random sample from some normal distribution where I don't know mu or sigma. I'd like to find a 95% upper confidence interval for mu. So from before, I know n equals 6. We've calculated x bar to be 3.92. We've calculated the standard error to be 0.9. I need the 95th percent quantile from the t distribution with 6 minus 1 degrees of freedom. So I asked R to provide it for me using that command, and it gives me 2.0151. So that's my Q value. And since I want an upper confidence interval, I'm going to copy and paste this thing down, replacing the values. So x bar minus q times s over root n would be the 3.92 minus that quantile, 2.0151, times 0.9 over root 6, and that gives me 3.18. So from 3.18 to infinity, I have my 95% upper confidence interval for the population mean mu, okay? All right. So let's look at a non-normal example. So pause, copy, and then play. So logically, we can also handle some non-normal things. So let's pretend we have a single observation from an exponential distribution with unknown parameter lambda. And we'd like a 95% lower confidence interval for lambda if our single observation was a 4. All right, well, there's the PDF of an exponential with parameter lambda. And as we've talked about before, if x1 is exponential with parameter lambda, then lambda times x1 is exponential with parameter 1. I'll call that lambda times x1 a new random variable y, okay? There's the PDF of y using lambda equals 1. And I'm going to go and find a 95% quantile for this new distribution for y. So I want 95% of the area to be from 0 to this unknown quantile Q, and then integrate the PDF over that interval. And I do some easy calculus, and then I do some algebra, and I solve my quantile to be 2.9957. So what that is telling me is that the probability that y is less than or equal to that quantile is 95%. Okay? Now, y is going to be my pivot variable because y is equal to lambda times x1. Y is a random variable that depends on lambda, but whose distribution does not. The distribution of y was exponential parameter 1, no lambda. Right, so I replace y with lambda times x1, and now I'm going to solve for lambda. So I can divide by x1. I don't flip the inequality because I know x1 is a positive number. So replace x1 with 4, solve, and that gives me a 95% lower confidence interval from negative infinity to 0.7489. Okay. All right. If I had wanted an upper confidence interval, I would have figured out the 5% quantile of the exponential distribution. So at what value Q is there only 5% of the area below it? Or, yeah, below it. He says, pausing carefully to make sure he's done this right. Yes, if I wanted an upper confidence interval, I'd have found that where the spot where 5% of the exponential distribution is to the left. That'd be 95% to the right, to the upper side. I'm on it. Cool.